Okay, it should be Monday, November 3rd. And yeah, we'll go ahead with the test on Tuesday, November 4th. You guys will be here in the morning. There's no reason we can't. I can't think of one other than you wouldn't want to. All right, question 55. Somehow 58 didn't get on the list. So you should be finishing up here today, 55, 57, 58, and 61. A clerk moves a box of cans, pulls a rope attached to the box, 185 newtons at 25 degrees. Box has a mass of 35 kilograms. Coefficient of friction between the box and the floor is 0.45. That's kinetic friction. So you got force of gravity on the object, which is the weight. Contact force, it's equal and opposite. It's going to probably move or accelerate this way. Now, if you could pull this force high enough, you could pull this guy off the ground. So you'd have to run another calculation to make sure that it's going to be that way, but it will. All right, so basically then you've got a net force, because it's got kinetic friction, so we know it's going to move, and if it's moving, we're going to end up with acceleration that way. So you've got a force to the right, subtract a force to the left, that's friction, and the force to the right is this side. So how that should look. So we're ultimately going to want to know the acceleration. So you got an applied force, which is from the red one here, which is what? Cosine, and a friction. But you also need a normal force to calculate friction. And the normal force is a combination of weight plus that. So what I've done is just find the normal force first. So if I move this one down here, my normal force would be this. So it'd be my gravity minus that. Now, I'm going to throw away my negatives here and not pay attention to the fact that gravity's down negative and this is up positive, because that'll get confusing. And all of this stuff going on is not in this direction of motion. So you really don't want to take those negatives into that other direction of motion. You're concerned about what's positive and negative here, not what's positive and negative in other dimensions. So you've got mass times gravity for this, and this side, if you took this over here, is 185 sine of 25, and you're going to make it that way. So what's left over from going down here plus this is 265 newtons for the normal force. Don't worry about it being positive or negative. I have it listed as a minus. Don't worry about that. So going to the next page. Now that you have the normal force, you can calculate the friction. Okay? So the friction is coefficient of friction times the normal force. We're going to subtract that off because it's this way, and our pulling force that way is 185 cosine theta. When you subtract those two, you get mass times acceleration. Acceleration works out to 1.4 meters per second squared. Number 57. This time you've got a block pushing up along the ceiling, I think, which is very similar to another problem where we were pushing it on a floor. So you got a 4 kilogram block pushed along the ceiling with an applied force of 85 newtons, acting at an angle of 55 degrees. And if it has an acceleration of 6 meters per second squared, they want the coefficient of friction. So you're pushing the block up against the ceiling like this is sliding along the ceiling. Okay, but we've got its weight. We've got a normal force this way between this and the surface. And we have an applied force that breaks into components this way and that way, and a friction this way. And the motion or acceleration could be in this direction. So whatever our applied is minus the friction is going to give us a net. So it's a lot like the last one, really. So the applied one is this side. So cosine 55 degrees times 85 is that one. The friction is coefficient of friction times the normal force, which is this. But that's a combination of two things, because you got this force that's applied up and gravity, which is down. So if you take this one minus this one, you probably get that one. So I have the applied and the force of gravity. I'm going to make that one positive and this one negative this time. And you're going to get 4 kilograms times 6 meters per second squared. We already have that. So we're looking for this guy. And once you put all the numbers in and solve for coefficient of friction, it's 0.816. And again, it'd be outside your probably capabilities on a test question to come up with this. So not only do you have to come up with this, you have to pay attention right here that you get that set up right. It's once you're showed how to do it, it's okay. Make sure you're thinking through the process. But it's probably not one I would give you one on a test question. Not that one. 58. A box rests on the back of the truck. The coefficient of static friction between the truck bed and the box is, what, 0.3 or something? And then you've got a maximum amount that you can accelerate before it starts to slide. So coefficient is probably static friction. It's not labeled that on my screen there. Static friction, yeah. I should have a subscript ST. And it's 35 kilogram box. So basically it's going to stick. So you add the forces up and you get 0 relative to the truck bed. So since they add up to 0, they're equal and opposite. So this static friction force is causing the acceleration. So it's the net force. So coefficient of static friction times the normal force is m times a. The normal force is m times g because we're horizontal. We don't have an angle we have to worry about this time. And it shouldn't matter the mass of the box. So the coefficient of static friction times g is equal to a. So the most we can accelerate is 2.94 meters per second squared, and then it'll start to slide one way or the other. And last one, 61. Coefficient of static friction between a 3 kilogram crate and a 35 degree incline is 0.3. What's the maximum force that must be applied to prevent it from sliding? Again, this is going to turn into an algebra problem that you might have a little trouble setting up. So we've seen a whole bunch of those. You won't have to worry, stay up and worry, are you going to have 6 of these on the test that you can't figure out? No, they'll be a little more straightforward. But you needed to see all these examples for various reasons. The last one, for example, there's a reason why you need to see that. Okay, so it can slide this way. So your equation needs to be static friction, something, they add up to 0. So your static friction is going to be all the other forces combined of friction. And your friction is going to be determined by the weight of it, plus something you're adding. So your downhill force, basically this one, has to equal the static friction. Now have this one done. Okay, here we go. Just get rid of this. And the static friction is coefficient of static friction times this applied plus that normal. And this normal is 3 kilograms times 9.81 meters per second squared times cosine 35. And at this point, you have everything else. You can't cancel an m out because that doesn't have an m in it. Don't make that mistake. So the downhill force is this one. It's mg sine 35. So once you have that set up, you just put everything in and solve for force applied, and it comes out to 32. So give that a try. Okay, a couple more things. Not in your book, they don't have an Arlene problem. If you had a trapeze artist, and let's just keep them in the middle this time. You can get more complicated and solve the two ends. I've never done that, but could. If you were solving a problem with Arlene and you want to know the force of tension, what you'd do if you put Arlene in the middle, half her weight is here and half her weight is there. So if she's 50 kilograms on this side, you'd use 25 kilograms times G to figure out that. And then it becomes like the clothesline problem. You figure out the tension force based on half of it, not the whole thing. And I'll let you noodle with that one. That can drive you crazy trying to figure it out. But just think about the buildings are each holding half. That has to be the case. And then it makes it easier to solve it. Okay, so wrap it up.